Hi everybody, it's Mrs. Derby here. We are in Algebra 1, Unit 6, and we're looking at 7.3. So we're going to look at some of these parabola shapes. That's the up and down, either the right side up U shape or the upside down, I guess, lowercase n shape. I don't know, something like that. And we're looking at 4 sets of descriptions and equations that represent some familiar quadratic functions. The graphs show what graphing technology may produce. So they're just telling us that they have already made the graph using like Desmos or something like that. And they're asking for us to describe the domain that's appropriate for the situation. Remember, domain is left and right, like doors. Okay, so remember, domain is what can our x inputs be from left to right. So that's our place that we're going to start there. Then we're going to think about upper and lower limits for the inputs and things like that so that it makes sense. We need to identify or estimate the vertex on the graph. Vertex is one of our new vocab words, and describe what it means, and then identify or estimate the zeros of the function, also kind of a new idea, okay, and what it means in this situation. So let's jump in and take a look. The area of a rectangle with a perimeter of 25 meters and a side length of x. Okay, so when I think about what's going to make the most sense, first of all, I'm going to use my nifty sticky notes to help me with domain, right? Domain is like doors. So I think about how far can I open the doors until I see the end of the graph to the left and the end to the right. Now, some of this is also going to be about what makes sense in this situation. So when we think about the vertex in this situation, if the side length of our rectangle, first of all, we can't have a negative length. So everything here doesn't make sense. I can't have a length of a rectangle that's less than 0. So going that way, I would have to stop at 0 because everything over there doesn't make sense. And if I'm talking about area of a rectangle, negative area also doesn't make sense. So if we're thinking about our context, not just our graph, but thinking about context, it's going to start making sense at 0. So our domain has to be with an x above 0. And in this case, it stops making sense here at, let's see, halfway between 10 and 15. So that's 12.5. Okay, so our domain makes sense only from here to here. The vertex is the very top that it gets. So this vertex, when I think about that, it's the peak of the graph, or if it's upside down, it's the deepest valley. This vertex looks like it happens right about here. Now this is going to be an ordered pair. Okay, so coordinates, that's what it means. So we look like we're somewhere between 5 and 7.5. We're almost right between those two. I'm going to say 6 because it's about right. Okay. It says to identify or estimate. So it looks like it's at about 6. And when I look up here, it's just below 40. So between 30 and 40, I'm going to say 38. Now it does ask me to describe what this means in the situation. So this is the largest area, okay? The largest area rectangle is 38 square meters. And we get that area when the side length is about 6 meters. Okay. Now, the zeros of the graph, those are my favorite things to look for because it's right here. It's where it hits the zero. Zeros of the graph are always where y is 0. So I can fill those in pretty fast. It's always where y is 0. So I already have, I see it happens 2 times. And so I need 2 numbers. One of them's here at 0, 0. And the other one's here at halfway between 10 and 15. Remember, it's this 12.5 right here. Now that won't always line up, but there we go. To describe what that means in the situation, it is the smallest area we can get. The smallest area rectangles are when the side is 0 meters and 12.5 meters. That's actually where we're going to like run out of whatever we're making the perimeter with. Okay. So there's our first one. I'm going to go a little bit faster for our next ones because there's a whole bunch of these. And then it actually asks you to work together to think about those. So let's see what else we've got. Number of squares as a function of step number. So we've got a pattern going on here. And it looks like, so if we had a pattern of squares, we might have that. And then the next one is a pattern of squares, and then it does something else. 1 squared plus 4, those kinds of things. So it's got this pattern that's going on. Okay. Now I see that this is an upside down parabola, so a U-shape parabola, or maybe think of that as right side up. This one has a domain if we're thinking about the number of squares as a function of a step number. That's saying that this is our step, our starting step, so our 0 step. And then this is our first step of a sequence. And then our second step of a sequence would have a 2 by 2 plus 4. This is our second step. Okay. So in this one, it looks like we can go backwards, and it looks like it's okay for us to just keep on going forever here. So it seems like our pattern lets us go backwards. A lot of times when we start a sequence or a pattern, we can't go backwards. So that's our idea. Like, I don't know what comes before the very first step of this sequence. So this one, I think we're going to start it just like this. That's as low as I can go. I don't have a negative of a pattern. So our domain starts at 0, but it could grow this way as long as we wanted it to. This graph keeps on going. So this goes up to infinity. And our vertex of our graph is the lowest of the low. It's here. It looks like it happens when x equals 0. And just to make sure, I'm going to go ahead and put it into my equation so I can figure out what that number is, because trying to estimate from 0 to 40, it's hard to tell what exactly number that is. So if I find what f of 0 is, 0 squared plus 4 is just 0 plus 4, which is 4. And that tells us that step 0, the starting step, has 4 squares. Now, this graph, when I look at the zeros is where it hits this y-axis down here, or the x-axis down here. This graph never, ever, ever crosses or hits that axis. So I would say none. We never have 0 squares is what that means, because this is our number of squares. We never have 0 squares. Number 3, distance in feet that an object has fallen t seconds after being dropped. This one is a lot like that, what we started with the building and dropping a rock off of it. So what I do know is that I haven't built a time machine yet. So negative time, again, doesn't make any sense. So negative inputs don't make sense. My domain is going to start at 0. And all of my x's, it looks like they can keep on going on forever. It's going to keep on doing that. Although at some point, it's going to hit the ground. So there has to be an end. I just don't know from the graph what that end point is. And here is our vertex, the lowest of the lows. Our vertex is happening at 0, 0. That means when I haven't yet dropped it, whatever that object is, when I haven't dropped the object, it hasn't moved at all. So it has gone 0 feet. It has not moved when I haven't dropped it. Whatever that object is. And the 0, the time where it's going to hit that x-axis, I keep saying y, when it hits that x-axis, is also 0, 0. That's where it's hitting there. So the only time that it hasn't moved any distance is when I haven't let go of the object. Or if I haven't given it any time to fall, it can't go anywhere. So this is no time to fall. Has gone 0 distance. Couple more. I think there's just one more to do, so let's go take a look. The height in feet of an object t seconds after being dropped. Okay, this is much more like the building and the rock that we're dropping off of it. So this is, again, always our starting point. So this is kind of the same thing in those exponentials. We had to start somewhere. This one starts at a certain height. Looks like that height is 576 feet. Now, again, I cannot go back in time, so can't have negative time. That I've let something fall. I also have another limitation to my domain. Okay, so I can't have anything over here. That's my boundary on this side. And if I'm dropping something off of a building, it's going to hit the ground right there. So this is where it hits the ground, and that's where it's going to stop. So nothing under here makes sense. I'm going to cross off that part right there. It does make sense to have an input from 0 to 6. So our domain is everything from 0 to 6 seconds. The vertex is the highest of the high points. That vertex is happening here. The highest high or the lowest low. This one is happening, let's see, right on that y-axis. So it's happening at 0. And if I put 0 in place of t, let's just go ahead and calculate that on a calculator. 576 minus 16 times 0 squared. 576. What that tells me about the vertex is that that's the height that I'm dropping it from. So the height I drop from. I spelled it wrong. So the height we drop from. And then the zeros of the function, I mean, there is one over here at -6, but again, that's not in our domain. It doesn't make sense. So the zeros always when y equals 0, right? It's like this idea of when is it going to hit this x-axis, and it hits when x equals 6. And so to interpret that and explain what that means, that is happening at time seconds. So at 6 seconds, this object has 0 height off the ground, and that means it hits the ground. The object hits the ground. All right, so different situations have different domains and vertices and zeros. Take a look at the lesson summary. It's going to tell you a little bit more and some ideas about how we would look at some of those limitations. And it's time to go look at some practice problems from lessons 5 and 7.